We're going to start today with alkynes, chapter 11 in our book. And you'll remember that alkynes are just carbon-carbon triple bonds with something else coming off either end. There's a couple of ways we can describe alkynes. So we can describe a terminal alkyne. So a terminal alkyne has a hydrogen at one end and some other R group at the other end. And an internal alkyne would be one that has two different, some sort of carbon groups coming off of them. So this carbon group over here could be anything, this carbon group over here could be anything, but it's an internal alkyne. You'll recall that alkynes have 2 degrees of unsaturation. So that means that there are 4 less hydrogens than you would find in a corresponding alkane. They're linear. So because of these sp hybridizations, they're linear and they have a 180 degree angle. So when you draw alkynes, you always want to draw them in a straight line and not bent or curved like you would with alkanes or alkenes. And lastly, they have 1 sigma and 2 pi bonds. So here's your sigma bond, and here are your 2 pi bonds. And that's what makes up an alkyne. If we talk about how to name alkynes, it's pretty straightforward. The nomenclature is the same as alkenes. So you're going to look for the longest chain that contains both carbons of this CC triple bond in them together, and that's going to be your longest chain that you're going to name as your root or your parent. If you have 2 triple bonds, you're going to name it as a diene, and if you have a double bond and a triple bond, it's going to be called an enine. That would be an enine. And an enine is numbered. You number the chain to give the first site of unsaturation the lower number, so that alkyne doesn't always have to have the lowest number. The alkene could have the lowest number, but whichever unsaturated carbon is closest to the end of your longest chain is going to be the way that you number your chain. Our smallest alkyne that we're going to meet looks like this, and its name technically would be ethine, but we're going to call it acetylene. That's its common name, that's what everyone calls it. So acetylene, just like a carbon-carbon double bond in our simplest molecule, is going to be ethylene. This one is acetylene. If we talk about physical properties of alkynes, they're going to be similar to alkenes and alkanes. So they're going to have low melting points and low boiling points, which are 2 different things, just a reminder. So low melting points, low boiling points. If you increase the number of carbons, then you're going to increase the melting point or the boiling point, because that's going to increase the number of van der Waals forces between the molecules. Also, if you think about solubility of alkynes, generally they don't have alcohols or amine groups on them. If you're just talking about plain alkynes, they're going to be soluble in organic solvents and insoluble in water. So those are our physical properties of our alkynes. We're not going to dig in too much. 7.4 today. I'm going to let you read it on your own if you'd like. It's properties of different interesting alkynes. So where they show up in our bodies and in nature and things like that. What are some important alkynes? Section 11.5 is the last one we're going to talk about today, and this is how do you make alkynes? So you already know this. You probably forgot, but I'm going to remind you and you're going to be great at it. So if you have a molecule that has two halogens on it, either both at the same end of the molecule or one at one end, one at one side, and one at the other side, you can use a strong base to remove two equivalents. So the one with both halogens on the same end is called a geminal dihalide. And this one over here is called a vicinal dihalide. Sometimes you'll hear the geminal one referred to as a gem dihalide. And it just means that both halogens are on the same carbon. If we introduce a strong base, so strong base being something like NaNH2, sodium amide, or our favorite one, potassium T-butoxide. And often that is in dimethyl sulfoxide as our solvent. So if we use one of these two strong bases, they will remove a hydrogen and a halogen and form a double bond, and then remove a hydrogen and a halogen again and form that second pi bond to make a triple bond. Looked at our first molecule that we had, and we add our strong base. After the first equivalent, you'll have something like this. And after the second equivalent, you'll have something like this. So that's our simple way of making alkynes. Now, you'll notice a lot of synthesis problems where you will take an alkene and you want to make it into an alkyne. And you will be tempted to want to do that in one step, but there's actually two steps to make an alkyne from an alkene. First thing we have to do is get our halogens on there, because we know that to make an alkyne, you have to have an alkane with either two halogens at one end or a halogen on each end. Right? So your BRs can be there, or they can be like this. You might remember that we know how to make this molecule that I've just drawn from an alkene. You would add Br2 in some sort of organic solvent. So CCl4 is popular, tetrachloromethane, or carbon tetrachloride. And so if you add Br2 to your alkene, you end up with a Br added on each end of the alkene, and then you can use your strong base to remove. Okay, that's not working. Hold on. You can use your strong base to remove the halogens. NaNH2, and you'll need two equivalents of that. So that's how we make our alkynes. And that's where we're going to end for today.